Controlled Environment Plant Production Engineering Technology Education modules are developed and presented by The Ohio State University, Rutgers, the State University of New Jersey, and the University of Arizona, with support from USDA NEFA through their Higher Education Challenge Grant program. In this module, we'll discuss the topic of measuring environmental parameters, aerial environment. This module is presented by Dr. Peter Ling of The Ohio State University, Dr. A.J. Both of Rutgers, Dr. Murat Kassira of the University of Arizona, Dr. Cherry Kubota of the University of Arizona, and Matthew Spies of The Ohio State University. The Measuring Environmental Parameters Aerial Environment module will allow you to meet 3 learning objectives. By the end of this module, you will be able to explain the importance of monitoring the greenhouse aerial environment, identify key parameters of the greenhouse aerial environment, and obtain high-quality sensor data. The main advantage of growing crops in a greenhouse environment, compared to the outdoor production, is the ability to control the environment. Plants in greenhouses are not subject to certain environmental stresses that are present outdoors. Sensors are the primary tool used in measuring greenhouse environments. They allow for optimization of crop production, enabling one to monitor and control key parameters in crop production. Increased control of growing environments can improve plant health by eliminating plant stresses and preventing potential disease threats. Proper use of these techniques can result in improved crop yields and also allow for the growth of some crop species out of season. Temperature information can be used for many beneficial applications. Heat and cold stress management can be used to avoid drought stress. Temperature affects the water content in the air, and water content affects the plant's transpiration capability. Temperature integration strategies can be used to save energy by only running temperature control systems when necessary. Temperature information can also be used to model plant growth and development strategies using indicators such as heating degree day and daily light integral. It is very important to measure temperature at the correct location for accurate results. The reading should be recorded at the canopy level and at a location representative of the entire growing area. It is also important to record the outdoor temperature. Humidity is another key parameter vital to plant growth. Obtaining the vapor pressure deficit is important when managing crop transpiration. Low humidity or high vapor pressure deficit typically increases transpiration rates, which can result in a loss of water or in the plant wilting. High humidity or low vapor pressure deficit reduces transpiration that could adversely affect water and nutrient uptake. Dry air pulls moisture out of the plants faster than the roots can supply water. Humidity can also aid in condensate management. Condensation on crops can be a big problem when it comes to disease. Any freestanding water on plant surfaces can be a breeding ground for disease. Condensation on glazing materials can cause a reduction of light transmission. Condensation on the ceiling of the greenhouse can also drop down on plants. As with temperature readings, it is important to place humidity sensors at canopy level and at a location representative of the entire growing area in order to collect correct readings. The proper management of light intensity and quality is of the utmost importance in the greenhouse environment. The portion of the electromagnetic spectrum that is useful for photosynthesis is wavelengths from 400 to 700 nanometers. Supplemental lighting in greenhouses is usually dependent on the amount of solar radiation received in the specific climate. Too much or too little light is not healthy for plant growth. Structural damage to chloroplasts can be caused by too much light. It is recommended that plants receive between 100 and 800 micromoles per square meter per second for about 12 hours per day. The level of light exposure is dependent on the species of plant. Light can also have an effect on plant morphology. For example, the control of the red, far red spectral ratio can be used to control plant height to a certain limit. As with temperature and humidity readings, it is important to place light at canopy level and at a location representative of the entire growing area. It is also very important to consider shading patterns when installing light sensors. You might record a significantly different reading if the sensor is in direct sunlight versus the shade. It is necessary to monitor carbon dioxide levels in the greenhouse environments to ensure proper respiration of the plants. Greenhouses need to be properly ventilated to prevent carbon dioxide depletion. Insufficient CO2 can inhibit plant growth. CO2 levels should be between 400 and 1500 parts per million. High CO2 levels are usually not harmful to plants, but can be harmful to humans. Toxicity to humans occurs between 1% and 10% and is likely to cause death. As with previous parameter readings, it is important to place CO2 at canopy level and at a location representative of the entire growing area. Airspeed often influences other parameters such as temperature and CO2 availability, as well as transpiration capability, leaf temperature, and boundary layer conditions. Certain air speeds can benefit or inhibit the growth of plants in certain ways. CO2 uptake is increased at air speeds between 0.03 and 0.1 meters per second. Optimal plant growth occurs between 0.5 and 0.7 meters per second, and plant growth is inhibited at velocities greater than 1 meter per second. When measuring airspeed, it is important to record a reading at the canopy level to ensure the health of the plants. It is also necessary to measure outside the greenhouse to make sure that the structure can handle the force of the wind. Changes to the greenhouse environment will be based on the data recorded, so obtaining high-quality data is vital to plant health. With all key parameters, it is important to measure where it counts the most, at the canopy level and at a location representative of the greenhouse as a whole. For example, sensors should not be placed in the corners of the greenhouse because that would only represent a fraction of the greenhouse environment. The air in the greenhouse should be properly mixed to ensure key parameters are at equilibrium throughout the structure. High-quality data can also be obtained by minimizing factors affecting measurement artifacts. Shaded areas can provide significantly different data than areas in direct radiation. Air temperature and humidity measurements also require a certain airspeed for accuracy. Other considerations include proximity to heat sources or sinks and the location of heating, cooling, or dehumidification equipment. The following slides show examples of correct and incorrect measurement techniques. We will show you some examples of good sensor placement. In this picture, the sensor is very near the germination tray that is being monitored. In this picture, the sensor is hung just above the plant canopy in a central location. The same is the case for this sensor and this sensor. In this picture, you can see a thermostat very near a heating unit. This is not good, as the thermostat will monitor heater temperature and not the plant canopy temperature. Residual heat radiation from the heater after it is turned off will keep the thermostat warm longer than the rest of the greenhouse. Here we have a picture of two separate heat systems, north heat and south heat, controlled by thermostats side by side. This system could be improved if each thermostat was moved to a location representative of the heater it controlled. This thermostat panel has been protected by foam edging so that people do not hurt themselves by running into it. This is a good safety measure. However, as you can see from the light and the shadow, this sensor is in direct sunlight. The sunlight will warm the thermostat, and the temperature reading will not represent the ambient temperature inside the greenhouse. This thermometer provides a good visual representation of greenhouse temperature. However, at the time the picture was taken, the greenhouse was a very comfortable temperature. This thermometer reads near 100 degrees, much hotter than the ambient temperature. This thermometer is located in direct radiation. Also, just to the left of the thermometer is a vent. When the vent is running, the thermometer will represent the temperature at the vent, not the plant canopy. In this picture, an indoor-outdoor thermometer has been placed on a windowsill near a window with sunlight shining through it. The outdoor temperature probe has been placed in the direct radiation. The indoor temperature probe is enclosed within the unit and is in the shade. As you can see from the readout, the indoor temperature reads 73.4 degrees, while the outdoor temperature reads 114.9 degrees. What is important to take away from this picture is that the sensor in the direct sunlight reads 41.5 degrees above the shaded sensor. Here is a simple demonstration of the effect of different shielding methods on the outdoor electronic temperature sensor from the direct radiation. The numbers shown represent degrees Fahrenheit above room temperature. In a styrofoam cup, the difference was 13.6 degrees Fahrenheit. When aluminum foil was wrapped around the cup, the difference was 11.6 degrees Fahrenheit. Foil only kept the difference at 10 degrees Fahrenheit. When the aluminum foil shield was aspirated with a fan, the difference dropped to 2.5 degrees Fahrenheit. This demonstrates the value of shielding and aspiration. In this picture, there is a reflective radiation shield over the thermostats. This is good. However, the thermostats are located very near a vent, which will make the temperature reading not representative of the rest of the greenhouse when the vent is open. Here is a picture of a shielded but not aspirated temperature sensor. Let's have a closer look at the panel so we can see the readout for this electronic temperature sensor. The readout states 92 degrees Fahrenheit, but a nearby expansion thermometer shows 82 degrees Fahrenheit. The electronic temperature sensor will be more representative if it were aspirated as well. This box shields the thermostats and aspirates them with a fan. It is important to consider here the heat the fan motor generates. If the air is moving from right to left, then the heat from the fan is being pushed into the box. That is not good. However, if the air is moving left to right, then the heat from the fan exits the box. That is good. Dust should be cleaned from the mesh on the left side of the box. This final image represents a very good configuration. The box has holes for ventilation and is located very close to the plants. There is a visual very near the electronic, shielded, and aspirated sensor. Thank you for viewing.